Topic 29, condensation polymers. This is the first part. So we're going to look at what a condensation reaction is first of all. So a condensation reaction is a reaction when two molecules react together and a small molecule, often water or hydrogen chloride, is eliminated. So let's have a look at the reaction of an alcohol and a carboxylic acid to make an ester in water. So it's a reaction that you might have come across at GCSE, and that is an example of a condensation reaction. So let's have a look at that first of all. There's our word equation here. So you can see here this is called a condensation reaction, and that's because the first set of chemists who did this experiment, they did this experiment in a test tube and they saw some condensation on the side of the test tube, and we have a molecule of water which was eliminated. So let's have a look at the actual reaction itself. So we're going to use R to represent the hydrocarbon chain. So that could be a CH3, it could be a CH3, CH2, etc. We're just going to write R though, because we're interested in the functional groups only. So here we have a carboxylic acid group. So it's a C double bond O, that's your carbonyl, and then an OH as well. Here we have an alcohol. So that's an alcohol there. I've put the OH towards the carboxylic acid because I know that this functional group is going to react with that one, so therefore I've turned it this way. Usually you would write it in the other direction. And I put a little dash there above the R to show that this is a different R group. So we can see when we look at the formula of the ester product, we know where this R group's gone and we know where that R group's gone as well. Okay, so that's your overall equation here, representing what's going on. Let's just change my colour here and highlight where these atoms go. So we have an OH and H here, and then an H on there. So this forms your molecule of water. So it's the OH which is from the carboxylic acid, and the H from the alcohol, rather than the OH from the alcohol and the H from the carboxylic acid. And that's all to do with bond strengths, okay? So it's the OH bond in the alcohol which breaks, and the CO bond in the carboxylic acid breaks, rather than the OH bond breaking in the carboxylic acid and the carbon-oxygen bond breaking in the alcohol. So it's this bond that breaks here, and that bond that breaks there. And that makes your molecule of water. So we've got H2O here. Okay. The carboxylic acid, that's this bit here. And in the formula of the ester, that's this bit. And then we've got this part of the alcohol here. And then the alcohol bit there of the ester. Okay, so I've kind of colour coded that there. We've got like a dark green here, a bluey colour, and then the red colour here to show what's happening here when we're making the product. Okay, so we're going to look at what we call condensation polymers. This is just a normal condensation reaction. We're now looking at condensation polymers. Condensation polymers are normally made from two different monomers, okay? We're going to underline the word normally. When we come to making polymers out of amino acids, they don't have to actually be two different monomers, but I'm going to write the word normally here and come back to that at a later time. So it's normally made from two different monomers. And each of those two different monomers has two different functional groups. So basically you've got a monomer with different functional groups on that monomer. So this is kind of how it works. So if we've got a monomer here, and on that monomer you've got a functional group, I'm going to represent it by a star there. That star there could be any functional group. On the other end of the monomer you've got another functional group. So remember, it's these bits of a monomer which react. Here we've only got one end of the molecule which is reactive. Here's the carboxylic acid end, and then the OH end of the alcohol, that's reactive here. But when we're making a condensation polymer, we have two reactive ends of the monomer. So you basically have a mono with two functional groups on it. And let's say if we take a second monomer, monomer B, call that, and we have two different functional groups on monomer B. What would happen then is monomer A can react with monomer B, and you can add lots of monomer A and lots of monomer B together because this functional group reacts with that one there. So essentially what you get is a long chain whereby this end of A would react with B here, and then this end of B here would react with A, and it would just keep extending the chain. Okay, so the chain would get really, really long here. And that's what we'll call a condensation polymer. At each monomer, what you get is you get a molecule of water or hydrogen chloride eliminated at each joint. And we're going to look at some examples of that now. Okay, so the first example we're going to look at is polyesters. But let's just write a little list of the condensation polymers that we're going to cover in this topic. Okay, so here's our examples of condensation polymers. So we've got polyesters, polyamides, and polypeptides. So we're going to learn about those. We're going to look at polyesters now, first of all. Okay, a polyester has something called an ester linkage. Okay, and the ester linkage links all the monomers together, and that repeats over and over again between each monomer to make the polymer. So if you look at a polyester, what you would see is you would see this C, and this is the carbonyl bit, the C double bond O there, and then an O coming off that C there, repeated right the way through the polymer. Okay, and we need to know how to make a polyester. So we're going to look at the two monomers that make a polyester. What we need is, the first thing that we need is we need a molecule which looks a little like this. Remember, there's no element A on the periodic table. That A would represent a hydrocarbon chain or a benzene ring or something. So we're just going to represent it as an A first of all, because we're just interested in the functional groups here. Now, this would be an alcohol. This is what we'll call a diol, because there's two alcohol groups. So the first thing you need to make a polyester is a diol. So this here would be a carboxylic acid, therefore that is a dicarboxylic acid. So those are the two things that you need to make a polyester with, okay? Right, okay, let's have a look at how this is actually made. Now, I'm going to need a little bit more space than this, so if you need to turn over and start a new page now, then now's a good time to do it, okay? So I'm just going to draw out my dicarboxylic acid again, just so I've got it on the same page. So here's my diol. And my dicarboxylic acid. Okay, remember that A and B would represent a hydrocarbon chain or a benzene ring or something like that. Okay, so let's have a look at this reaction. So what I'm going to do now is I'm actually going to draw how I'm going to form this polymer, okay? And this polymer, remember, is a polyester. I'm going to draw 2 diols and 2 dicarboxylic acids. That's kind of roughly what the thickness of my page is here. But obviously, in reality, there'd be millions of these. But I'm only going to draw 2 of each just to show how that polyester chain is made. Okay, so what we've got here is we've got a diol, dicarboxylic acid, a diol, and then a dicarboxylic acid. So I'm going to link this diol to that dicarboxylic acid, and this end of this dicarboxylic acid to this end of the diol, and this end of this diol to this end of the dicarboxylic acid. I'm not going to link anything to this end of this diol or this end of this dicarboxylic acid, but in reality you would imagine that here you would have another dicarboxylic acid, and here you would have another diol, and that pattern would keep on repeating. Okay, but if I can show you 1, 2, 3 links, so I need 4 molecules, and I'll show you 3 links here, then you'll see what's happening. So what happens is, just like when a carboxylic acid reacts with an alcohol, a molecule of water is linked at this point here, then between each of these links, a molecule of water is eliminated. Let's show you what happens here. So remember, it's the OH from the dicarboxylic acid and not the OH from the water, which makes the water molecule. Remember, this bond here breaks between that O and the H, and this bond here breaks between the C and the O. Let's remind ourselves on of this. Remember, it's the OH bond here in the alcohol and the CO bond here in the dicarboxylic acid, or the carboxylic acid in this case. And make sure we do the same thing here. So here is our first molecule of water. So what I'm doing is I'm connecting this O here, to that C there, and eliminating the molecule of water. And then let's look at this one here. So this time I'm breaking this bond here and that bond there. So remember, I'm linking this carbon here with this oxygen here. So it's the carbon on the carboxylic acid, or the dicarboxylic acid in this case, that links to the oxygen on the alcohol. You might want to write that down in words. So it's the carbon on the carboxylic acid, or the dicarboxylic acid, which links to the oxygen on the alcohol or the diol. Okay, what I'm going to do now is, now I've produced my 3 molecules of water for these 5 monomers, and now I'm going to draw the polyester here, and I'm going to link together that oxygen with that carbon, I'm going to link together that carbon with that oxygen, and I'm going to link together that oxygen to that carbon. Now you've got to be able to draw these based on what monomers you're given. So you might want to practice changing what A is and what B is, but the same principle applies. Now I know that this H here is going to be part of another water molecule, but I don't want to draw this one here, so I'm just going to put like a box around it like that to show that it goes off in this direction, maybe the start of an arrow or something. I'll do the same thing over here. Remember, that's the CO bond that breaks here, so I'm going to draw my box there like that. So when I draw my polymer, I'm going to draw an O here with a bond coming out of it like that, with nothing actually on the end of that O, but we know that that O will be connected to something, and it will be the carbon of the dicarboxylic acid that would have been here. But I can just draw a line with nothing on the end of it. So we've got O, A, O. Now be careful, don't draw the H, because that's been eliminated. Don't draw this OH, because that's also been eliminated to make the molecule of water. This O is chemically bonded to that C. That's a new bond that I've formed there. B, CO, then stop, because I've broken that bond. That C is chemically bonded to that O. A, O, CO, B, CO, and then that bond's broken, so I'm just going to draw a line like that to show that the polymer keeps going on like this. Now, you might have remembered these from GCSE. What we do now is, with this bond here, is we draw a line sort of through it like that if we want to show that this is a polymer. But in this case, I've drawn more than one repeating unit, so I wouldn't do it in that particular case. You only really draw the square brackets down these things if you only show one repeating unit. So one repeating unit here would be where you've got the dicarboxylic acid monomer and the diol monomer as well. So it would be kind of here, okay? But because I've got two repeating units here, then I don't need to draw the square brackets. So what we've got here is a polyester. Now it's not particularly named this polyester because A and B are just general alkyl groups. Okay, so we can't actually name this, so we just write polyester in there. Now, there is a few monomers and polymers that you need to know the structure of, and the ones that seem to come up quite a bit, and we're going to look at one of these now, okay? So we're going to look at a fibre, right? And this fibre is called pterylene. You might have come across this before. So this is the fibre tellurine, okay? So I'm going to draw the general equation here in words, and then I want to use this page here to draw the structure of what tellurine looks like. So tellurine is basically made from a dicarboxylic acid and a diol. So let's have a look at our structure of a diol first of all. The diol is called ethane 1,2-diol. And the dicarboxylic acid is benzene 1,4-dicarboxylic acid. And that makes pterylene. The reason why we call it pterylene and not the full proper name is because this is actually trademarked, okay? A bit like Kevlar, for example. That's also trademarked, and I think nylon is as well, or it was. Okay, so let's have a look at this reaction. So here we've got our diol. I'm going to draw my diol, ethane 1,2-diol here. When I'm doing this here, can you just refer back to this all the time? So here's the general equation, if you like, and this is a specific equation here. So here we've got our diol. So this A here is just a CH2CH2. And this is ethane 1,2 diol. Ethane, because there's 2 carbons. Off carbon 1 and carbon 2, I've got an alcohol group. There's 2 of them, so I write diol here. So I've got a benzene ring in here. So B, in this case, is just a benzene ring. So it's called benzene 1,4-dicarboxylic acid. So I have a carboxylic acid group here. Positions 1 and 4 on this benzene ring. I'm only going to draw 1 monomer of each. So remember, it's the OH bond which breaks in the alcohol, and the CO bond which breaks in the carboxylic acid. So that would go off and make a molecule of water. Okay. And this bit of the OH wood as well, connected to another monomer over here. And at this end as well, the CO bond would break and go off and make a molecule of water with the next monomer. But we're just going to link these 2 monomers together. So I've got a bond here coming off the O, CH2, CH2, O, and that O is chemically bonded to that C double bond O, benzene ring, C double bond O, and that C double bond O will be connected to another monomer there. So what I've got here is I've got a repeating unit. And because I've got a repeating unit, what I can do is I can just put a line that dissects that there like that and write the little symbol N, and you would have seen that at GCSE. This is our repeating unit for terylene, which is a polyester. Okay. Right, let's have a look at a polyamide now. So we've done polyesters, now let's look at polyamides. Okay. Let's remind ourselves how to make an amide. Know how to make an amide first before we start with a polyamide. So an amide is formed when a carboxylic acid and an amine reacts together. Let's have a look. So here I've got a carboxylic acid. Here I've got an amine, and that'll make an amide. And a molecule of water. Let's see where these groups came from. So we've got a molecule of water here where this bond breaks, the CO bond in a carboxylic acid breaks, just like it does when you make an ester. And that NH bond breaks, just like the OH bond breaks in an alcohol. So there's our molecule of water. And this bit here of the original carboxylic acid ends up in the amide, and this part here of the amine ends up in the amide there. That's how you make an amide. So a polyamide has the linkage, an amide linkage in it. This is what an amide linkage looks like. So the C double bond O, NH, there's the NH, and then we've got an R group coming off here, and an R group coming off there, okay? So polyamides have this, you see this linkage in them, repeating itself between each monomer, okay? So to make a polyamide, we need a diaminoalkane, which has two amine groups, and a dicarboxylic acid, which has two carboxylic acid groups. To make a polyamide, we need a diaminoalkane, which is two amine groups, and a dicarboxylic acid. Which has two carboxylic acid groups. Okay. Let's have a look at a general equation first of all to make a polyamide. So we need a diaminoalkane. Sometimes we can just call that a diamine. Put that in brackets. And a dicarboxylic acid. So let's draw diamine. So that would be an amine. This is therefore a diamine or a diaminoalkane. It's the same thing. Here we've got a carboxylic acid, and here we've got a dicarboxylic acid. Okay, remember it's the NH bond which breaks and the CO bond which breaks in the dicarboxylic acid. So here we have a molecule of water eliminated there. Let's link these together. And before we do that, let's just make sure that we've broken this bond here, because that will go off and react with another dicarboxylic acid over here somewhere. And this bond here would break, reacting with another diamine somewhere over here. Okay. So let's draw my polymer chain. I like to draw polymer chains nice and straight with all the bonds in one plane. I'll show you what I mean by that. So over here, you've got this N bonded to nothing. In reality, we know that that N there is actually bonded to another carbon of a dicarboxylic acid over here. So notice I'm drawing all the bonds in this plane along here, apart from the odd group which I'll put vertically up. That's a good way of drawing a polyamide. So we have an NH, A, NH, that N is chemically bonded to that C double bond O. B, C double bond O, and that C double bond O is probably bonded to another N over here somewhere. So I'll just draw that line like that. And that there's our repeating unit, like this. And that's what we'll call a polyamide. Okay, so the ones that you need to know, polyamides that you need to know, are nylon 6,6, and Kevlar. They're the ones that you need to know. They're the polyamides that you need to know. Okay, let's have a look at that as examples. So first of all, what we'll do is we'll look at nylon 6,6. Okay, you're going to need probably quite sort of a bit of width here on your page, I think. I'm going to use this margin as well. So remember, we've got a diamine, a dicarboxylic acid. So what we've got now is, after this, we've got 6 CH2s. Okay, let's name this now. We've got 6 carbons long, so it's going to end in hexane. And we've got these amine groups on the end. So we've got an amine group on carbon 1 and an amine group on carbon 6. So we've got 2 amine groups. So we write diamino. And we need to say where those amine groups are. There's one on the first and one on the 6th carbon. So it's 1,6-diaminohexane. So here is our diamine. So we've got a carboxylic acid group, including this carbon here, and then another 4 additional CH2s in between. So that's 6 carbons long in total, though. So we've got 6 carbons long in total. 1, 2, 3, 4, 5, 6. 4 of them are CH2s here. Then we've got a carboxylic acid group on each end. So because it's 6 carbons long, it's going to be hexane. At this time we put these groups here on the end of the molecule. That's because they take priority over the hexane bit. So we've got a carboxylic acid group at carbon 1 and a carboxylic acid group obviously on carbon 6. So it's hexane 1,6-dicarboxylic acid. That's the name of our molecule. Okay, so what we're going to do is we're going to link this carboxylic acid, this diamine to that dicarboxylic acid. So it's no longer an NH2 on the end here, it's just an NH with the bond coming off. We've got 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons long. And they're all CH2s. and an NH here, like that. And then that NH here is chemically bonded to that carbon there. Remember, I've taken that OH and one of those H's to make a molecule of water at this link point here, plus H2O there. Then after this C double bond O, you've got 1, 2, 3, 4 CH2s. And then a carbonyl again. Remember, I've used that OH to make a molecule of water, so I'll just draw a line there like that. So it's quite a big repeating unit, this, isn't it? So that is a repeating unit of this particular polyamide. Put a little N there. And that is nylon 6,6. The reason why we call it nylon 6,6 is because you've got 6 carbons here and 6 carbons there. Yeah, you can also get nylon 610, which has 10 carbons in one of the monomers. We're just going to look at nylon 6,6. So nylon 6,6 here is made of 1,6-diaminohexane and hexane 1,6-dicarboxylic acid. If you want to make nylon 610, this is what you would need. So you would need probably 1,6-diaminohexane again. And instead of hexane 1,6-dicarboxylic acid, you would need decane, I suppose that's 10, 1,10-dicarboxylic acid. And that would make nylon 6,10. Okay. Now your task, you do this yourself. I want you to draw that out, just like I've done here for nylon 6,10. So draw your 2 monomers, and then your repeating unit polymer chain here. So I want you to draw that. Okay, so let's have a look at Kevlar now. So Kevlar is another example of a polyamide. So we've got nylon here, nylon 6,6 here, and nylon 6,10 there. We're going to do Kevlar on this side, which is another example of a polyamide. So that there would be an amine. Therefore that is a diamine. We've got a dicarboxylic acid there. Let's name these. Got a benzene ring in the middle here, and then an amine group coming off at carbon 1 and carbon 4. So it's benzene 1,4-diamine. And this one here, what we've got here is we've got a benzene ring with a carboxylic acid group coming up off carbon 1 and then one coming off at carbon 4. So it's benzene 1,4-dicarboxylic acid. And let's link these monomers together. So remember, it's the NH bond which breaks here and the CO bond which breaks there. That's your molecule of water. So let's draw Kevlar in this space here. NH here, benzene ring, NH, and the N is chemically bonded to that C double bond O. Benzene ring, C double bond O, and that C double bond O will be bonded to another N over here somewhere. So that's our repeating unit, and that is Kevlar, which is a polyamide. Okay, so Kevlar has got very different properties to nylon. So nylon obviously you can bend around quite easily. I mean, Kevlar is relatively flexible, but Kevlar, you might use it to make like a helmet or a bulletproof vest or something. It's much stronger, and that's because these aromatic rings here, they can pack together, and what happens is that packing together the strong intermolecular forces between these benzene rings, and what that does is that makes the whole thing quite strong, okay? But the chains are still able to slide over each other quite easily, therefore it's flexible. So you've got like a strong material which is still flexible, which is great. So that is basically how you make Kevlar, nylon, and terylene as examples of polyesters and polyamides. Okay, so what we're going to do next time is we're going to look at how you make polypeptides. So in part 2, we're going to look at how we make polypeptides.